When a wave encounters a boundary between two different materials, two different media, or two different materials, one of two things can happen. We can, one, get reflection. Reflection means that the wave bounces back. And the reality is, when a wave hits that boundary, well, we'll always get at least some reflection. The other thing that can happen is transmission. We will also always get some transmission. There will usually be more of one than the other. We'll usually get mostly either transmission or mostly reflection. Well, when do we get which? We get mostly reflection when the materials are very different from one another. For instance, yesterday we did the little demonstration with the slinky. When the slinky wave hit air, slinky and air are very different from one another. So most of the wave reflected. Some of it would have went into the air, but most of it reflected. When the slinky wave hit Rutger's hand, most of the wave reflected because the slinky was very different from Rutger's hand. If we were to attach two slinkies together, send a wave down one slinky, what would happen when it hit the boundary between that slinky and the other slinky? Well, most of it would keep going because the two slinkies are very similar. Most of it is transmitted when they're very similar. Most of it is reflected when the two materials are very different. Let's take a look at the part that's reflected. It can be reflected in one of two ways, either right side up or upside down. Can anybody tell me when the wave is reflected right side up or upright? Think back to the demonstration yesterday, okay? When you saw the wave coming back on the same side as it went down, what was happening? Was it going from slinky to air, or was it going from slinky to Rutger's hand? Bailey, what's your answer to that? So when it's going to something more dense? No? Travis? The other way around, right? It's going from something more dense to less dense. In other words, it's not attached. Okay, when the slinky is going from, or when the wave is going from slinky to air, slinky wasn't attached to anything, we found that the wave is reflected back on the same side. When it was going from slinky to Rutger's hand, it was going from something less dense to more dense, or something that was fixed, something that was attached. We're going to find that it's reflected upside down in that case. Does that make sense? So it's either right side up or upside down. Visualize the picture. Okay, you guys all saw this yesterday. Okay, we saw the wave going back on the opposite side when Rutger was holding on. Okay, so we know that it's inverted when it's going to something that's more dense. Rutger, we're not trying to call you dense here. Okay, we're just saying physically, you have a higher density than the slinky has. Okay, when it's going from something less dense to more dense, in other words, it's attached, it's going to be reflected upside down. And similarly, when it's going from less dense, more dense to less dense, like it's going from slinky to air, it's going to be reflected right side up. What about the law of reflection? This comes into play when the wave hits a boundary at an angle. Let's say the wave hits it at an angle, let's say of 24 degrees. What does the law of reflection tell us? Josh? Yeah, good. It's going to reflect at 24 degrees every single time the law of reflection holds. Record question? Yeah, absolutely. It's going to reflect, obviously, if this is our normal line here, it's not going to reflect back at the same angle this way. It's going to reflect at the same angle on the opposite side of that normal line. Yep. That's it. That's the law of reflection. That's easy enough. You guys knew that in grade 5, for heaven's sake. You might not have known how to express it in grade 5. You might not have known that it was a physical law, but at some level you knew that if something bounced off of something else, it would bounce off at the same angle that it struck it at. Okay, that's the law of reflection. Well, what happens to the part of the wave that doesn't reflect? Because we know that some of it's always going to reflect, some of it's always going to be transmitted. Sometimes you get more of one than the other, but you're always going to get some of both. Well, when the wave is transmitted, when the wave keeps going, there's 3 things that can change. Something always changes. What's the big thing? What's the most important thing that always changes there, Jace? Good. The speed changes. That's the most important one because that's what causes the other things to change if something else is going to change. So let's label speed first. What else also changes? Rutger? Good. If the speed goes up, the wavelength will go up. If the speed goes down, the wavelength will go down. What else also can change? Doesn't always change. Depends upon how the wave strikes the boundary. Good. If it's at an angle, then the direction will change. Good. I'm glad you said that if it's at an angle thing, because the direction doesn't always change. If this is my boundary and it strikes it like this, it's going to change speed when it goes into the new medium, and it's going to change wavelength, but it won't change direction. If it strikes the boundary like this, it's going to change speed, it's going to change wavelength, but it's also going to change direction. If it goes in at an angle, the direction will change as well. And that's a result of the speed changing, right? I gave you guys the soldier analogy yesterday, right? Marching on pavement, marching in the swamp. What happened? Well, the speed changed. That caused the wavelength to change. And it also caused the direction to change because they entered that swamp at an angle. Yep. That's a good question. It shouldn't. No, it shouldn't unless there's some way for the energy to be lost. Okay, but
let's say that it's like wave.
Okay, absolutely, yes. If it's something that dissipates the wave, yes, then you would lose energy and therefore you'd lose amplitude, yes. But I suppose that would depend upon the nature of the material. The idea of it changing speed when it goes from one medium to the other, it's called refraction. That doesn't cause it to lose amplitude, doesn't cause it to lose energy. Now, there may be another reason why it could lose amplitude and energy, okay, but it wouldn't be because of the change in speed. Okay? What stays the same? What always stays the same? Once a wave has been made, this never changes. We did a question, I think, like this yesterday, where a musical instrument, I think, above ground and then below water. The speed was dramatically different, right? The speed below water was higher or lower? It was way higher, right? Because the particles of the water waves were a lot closer together. It was way higher. But what didn't change? The frequency. Once a wave has been made, okay, you blow into that horn or you pluck that guitar string. Once a wave has been made, the frequency of that wave doesn't change. The wavelength will, the direction will, the speed will, but the frequency doesn't change. Good? We finished off yesterday with another kind of interaction. This time, the wave isn't encountering a boundary between two different materials. This time, the wave is encountering another wave. What happens when a wave encounters another wave? Well, we get a phenomenon called interference taking place. There's two kinds of interference. What were they? What were those two kinds of interference, Josh? Be careful. Constructive, and not deconstructive, but rather destructive. You know what, Josh? I probably would have marked that right on a test. You know what you're talking about. You just missaid the word. Constructive and destructive. When does constructive interference occur? There's two situations in which we can get constructive interference. Constructive interference in which we get a wave that's bigger than the waves that encountered each other. When does that happen? Right? Okay, the waves are on the same side of the equilibrium position. In other words, a crest meets a crest, crest and a crest and a crest, or a trough and a trough. If these two guys meet each other, then we're going to get constructive interference. We're going to get a really big crest. We saw that yesterday in the little demonstration we did. If two troughs hit each other, we're going to get a really big trough. That's also constructive interference. Destructive interference occurs when we get a crest and a trough. Okay, and sometimes you get partial destructive interference where the wave becomes smaller. Sometimes you get total destructive interference where the wave is non-existent. For a short period of time, it disappears. We talked about noise-canceling headphones yesterday. Remember that? Okay, half of you had noise-canceling headphones. The idea behind noise-canceling headphones is that although the sound from the outside comes in through those headphones, goes into your eardrum, you should be able to hear that, right? The thing is, though, the noise-canceling headphones actually take that sound, electronically record that sound, and then spit out that sound or spit out the opposite of that sound, so that essentially whenever we have a crest that's coming in from the outside, the headphones actually produce a trough to cancel it out. Whenever we have a trough coming in from the outside, the headphones actually produce a crest to cancel it out. So it's kind of weird, but to cancel that noise from the outside, what the headphones are actually doing is making more noise. So it's kind of double the noise. But if it's at the right time, in the right phase, then crest meets trough, and they cancel each other out, and you don't hear a thing. Does that make sense? I said crest meets trough. It's not really crest meets trough. It's really talking about sound waves, right? So it's really compression meets rarefaction, right? Because sound waves are longitudinal waves. It's easier to think of it as crests and troughs, though. This was constructive interference, get a bigger wave. This one we did yesterday was destructive interference. We get a small wave. Do you guys remember how to do these? Let's just take a look at a couple of points here, okay? Just a couple of points. Okay, on this one where we get destructive interference, okay, the wave produced right here will be right here. The wave produced right here will be right here. That makes sense? There's nothing to interfere with over here or over here. The only interference that takes place is in here. Let's take a look at a couple points inside there. This one is 2 above, plus 2. It's 2.5 below, minus 2.5. What do they combine to give me? 2 and minus 2.5. Negative 0.5. We're not averaging them. We're just adding them. What about this one? This one's about 1 above and about 3.5 below. 1 plus negative 3.5 gives me negative 2. Do we divide that by 2? Do we average those? No, we just add them. So it's negative 2.5. Once we've done all of those lines, what do we do with them? Join them together. It's going to look something like this, although you'd have a lot more data points to connect there. We end up with a smaller wave than we started with, therefore we'd say it's destructive interference. Does that make sense? Good. You guys okay with that stuff? Excellent. Okay, the topic of today, and this is a pretty small topic actually, it's called diffraction. Diffraction is the spreading out of a wave. We defined refraction as the bending of a wave, right? Yesterday, we drew that picture, or a couple of days ago. Was it yesterday or a couple of days ago? We drew that picture of the soldiers. Yesterday, I think it was, isn't it? Okay, we drew the picture of the soldiers, right? The wave front bent. The bending of that wave was called refraction. The spreading out of a wave is called diffraction. Well, when does a wave spread out? If there's an opening, then the wave will spread out. When I talk right now, there's people in the hallway that can probably hear me right now. When the sound wave that's coming from ultimately my larynx, my voice, hits the wall, for the most part it reflects and bounces back into the room. But when it gets to the doorway, it goes out the doorway. But it doesn't just go straight out the doorway, so that somebody right in front of the door is the only person that can hear me. It diffracts, or it spreads out around the doorway. When a water wave encounters an opening, sometimes you see kind of an artificial harbor built in an ocean. And what they'll do, because let's say you've got this landform right here, and you want to build a harbor right here. Well, what they'll do is kind of build this breakwater out here out of rocks and concrete to prevent these big waves crashing in to these boats that are docked in here. Well, what happens right here? As the water waves are coming into the shore, they encounter that opening. And when they go through that opening, they spread out. Diffraction is the spreading out of the wave. Here's the wave. It encounters that opening. It doesn't just go straight through there. It spreads out something like this. This make sense? Diffraction is the spreading out of the wave as it goes through an opening or around a barrier. Now, there's a couple of things that will affect the amount of diffraction that takes place. The size of the opening, the frequency of the wave, the wavelength of the wave. The smaller the opening, the more diffraction you will get. In other words, it's going to spread out more. show you a picture of that. So you got, let's erase this one for a second. So you got a situation like this, where you've got an opening that's quite large. Let's say it's water waves, although it doesn't have to be water waves. It can be whatever kind of waves we want. These water waves are approaching this barrier. Okay, the water waves that hit the barrier reflect back, but the water waves that hit this opening keep going through. Those water waves will spread out. They'll spread out something like this. Now you can see that they're spreading out there, but they're not spreading out a great deal. If we have another barrier where the opening is really small, and we have the same water waves approaching that barrier, then again, you're going to get most of that water wave reflecting back off of the barrier, but the part that goes through will spread out, just like it did before, except it's this time going to spread out a lot more. You're going to get a lot more diffraction taking place because the size of the opening is smaller. Does that make sense? A small opening is more like dropping a rock into the water. When you drop a rock into the water, what happens? You get a complete circular wave formed, right? That circular wave goes out around it. Okay, when you drop a rock into the water, you don't just get part of a wave like this, you get a complete circle formed. Okay, when we have a really small opening, it's kind of like dropping a rock into the water. The smaller it is, the closer it is to being like a single rock being dropped into the water, and the closer you get to having a full circle of waves. So the smaller the opening, the more diffraction takes place. What about the frequency of the wave here? Rucker, question? I'm sorry? No, that's a good question, though, Rucker. That's a really good question, but it's not similar to that. The mist nozzle on a garden hose, or sometimes even you just put your, you don't have a garden hose nozzle, and you just have the opening, right? And you put your thumb over it if you want it to spray further, right? That has nothing to do with diffraction, although it's a really good thought. That has everything to do with pressure. In grade 9, I think it was, you learned about pressure. Pressure was equal to force over the area. Well, there's a certain amount of force that the water is being pushed out with by, well, if you live in the country, by the pump that's in your basement, okay? Or if you live in town, it's the water pressure that the town sends the water to your house with. Okay? If you decrease the area by putting your thumb over it, right, then it decreases the area. That's going to increase the pressure, and it's going to spray further, right? Same thing with a shower. Okay, I remember years ago, I went to visit my parents for Christmas, I think it was, in Nova Scotia, and my parents had the shower nozzle that was like the water was just kind of pouring down, dripping down. It was no pressure at all. It was terrible. And I remember saying to them, like, well, why don't you fix that? And Mom's like, well, how do you fix it? Like, how do you fix a shower nozzle? And I said, well, just either get a new shower nozzle or just use CLR or something to unclog it. And in the end, you want to have the holes the size that it's supposed to be, okay? Because the surface area of these holes is going to affect the pressure. So when you've got a mister or a yeah. Yeah, no, I see what you mean, but I still don't think that would be it. I think it would be the pattern of the holes that are on that mist nozzle, right? Small holes are going to give you more mist, right? It's going to spray with more pressure, but the direction of it, I still think it's the way the holes are made. I think. No, because you don't have waves there. It's just a stream of water. So I don't think that's it, Rucker. It's a good question, but I don't think that that's it. What about the frequency of the wave? That's another thing that affects it. This is one, honestly, when I was in grade 11 and I learned this the first time, I had the toughest time remembering how the frequency of the wave changed it, how the frequency of the wave affected diffraction. In fact, even when I started teaching this, I could never remember. In fact, right now, if you were to ask me right now and not give me 5 seconds to think about the answer, I couldn't tell you how frequency affects diffraction. I don't remember. Okay, I never remember this one. Never do. But early on when I started teaching, I figured out a way to figure out how diffraction is affected by frequency. When I moved here, I lived in an apartment just below the hill, just below OJ, Okotoks Junior High School on the hill. It's these brown apartments. Back at the time, that was like the only apartment building in town. Every teacher that moved to town lived in this apartment building. It was kind of like a dorm for teachers, almost. Anyways, I lived in this apartment building, and I would always, back before I got married, I would always fall asleep to talk radio at night. I would always turn on the radio, set it for a sleep timer of 60 minutes. I would always fall asleep long before the 60 minutes was up and before the radio shut off by itself. Okay? But it would just, the talking would help me fall asleep. So I found this radio show that I liked on AM radio, and I can't even remember what it was. It was some call-in talk show that I liked on AM radio, and it was on at like 11 o'clock at night, I think, something like that. So I would listen to this every night, and I would fall asleep to this every single night. And then one night, it wasn't there. One night, there was some other program on, and I'm like, well, now how am I going to fall asleep? I don't have my talk radio to fall asleep to. So for a few days, I'm like, I can't do this. I can't fall asleep now because I don't have my show. I don't have my radio show to fall asleep to. I flipped through all the other stations, can't find it. Okay. So then one night, I'm driving back from school. I was at school late one night, driving back at 11 o'clock, and I've got the radio on an FM station. And all of a sudden, there's my show. So I figure, okay, that's perfect. They've just switched it to an FM station. I'll go home, I'll tune in my radio to the new FM station, and I'll listen to my radio show, and I'll fall asleep just like I used to. I tuned into the FM station, couldn't hear a thing in my apartment at the bottom of the hill. Couldn't hear a thing. It wasn't just the radio, that call-in show that I didn't hear. Couldn't hear anything. The radio station just wasn't coming in. Well, it took me a little while to figure out what was going on, but in the end, it was a diffraction thing. And in the end, that's what gave me the way to remember how frequency affects diffraction. That's how, to this day, I still figure out how frequency affects diffraction. Here's the hill. It's not quite that steep, but here's my apartment building at the bottom of the hill. Here's my car over here. My car didn't really look like that either. Yeah. Although it wasn't very nice. It wasn't a very nice car at the time, but it didn't really look like that. Over by where JP2 is now. That's where our school HTA used to be. Here's the radio waves. Here's the AM radio waves. AM, by the way, means amplitude modulation. AM radio waves are in the range of kilohertz. That's a big frequency, but it's a smaller frequency than FM radio waves, which are megahertz. These are thousands of hertz. These are millions of hertz. So FM is clearly a much bigger frequency than AM radio waves. See, when I used to fall asleep to this radio show on AM radio, there was a small frequency. In other words, the waves were relatively far apart. Okay? High wavelength, small frequency. Those waves would diffract. And those waves would go right through my apartment, and I could tune in my radio to listen to that radio station. I could also hear it in my car over here as well, right? I had no problem listening to AM radio either in my car or in my apartment. But if we all of a sudden switch to FM radio waves have a much higher frequency and a much smaller wavelength. FM radio waves would look more like this, much closer together. Higher frequency, much closer together. Those FM radio waves will also diffract, but they diffract less. High frequency diffracts less than low frequency. You can see that those high frequency radio waves, those FM radio waves, can be detected across town. That's why I could hear the FM radio station in my car when I left school that night, but I couldn't hear it when I got home and tuned in my radio in my apartment. So let's go back to this page. How does frequency affect the amount of diffraction that takes place? Smaller frequency more diffraction. How do I remember it? Because I could listen to AM radio at the bottom of the hill, but I couldn't listen to FM radio at the bottom of the hill. That's the only way to this day that I can remember that smaller frequency gives me more diffraction, because I could listen to my radio show on AM, but I couldn't listen to my radio show on FM. Finally, what about the wavelength? Well, we know that V is equal to F times lambda. Wavelength is equal to V over F. If frequency goes up, wavelength goes down. They're inversely related to each other. So if smaller frequency causes more diffraction, then bigger wavelength causes more diffraction. You want more diffraction? Decrease the size of the opening. Decrease the frequency. Increase the wavelength. Increase the distance between the waves. All right, that's it for today.